mode. And the recording has started.
Perfect. I heard that perfectly. And Bonnie, would you mind testing your audio as well to make sure?
Sure. Hello, everyone. My name is Bonnie Acosta. Can you hear me?
Yes, we can.
Yes.
Both of
All right.
you are ready to go.
Great. Thank you
We
so
can hear
much.
you very well.
Okay, great. Sounds good. All right, I have my pointer ready. Okay, so let's get started with this. So I'm gonna present ourselves very briefly, and we have also a slide showing who we are, our team here in College Park, Maryland. We're at ANSEP. So as Jordan mentioned, my name is Jose Galvez. I've been working here at the WPC International Desks, which is a program inside NOAA, in mostly training on weather and climate forecasting for the Americas. Our main goal is to train the Americas, but we also look at other parts of the world. And as Jordan mentioned, part of our emphasis is working on satellite data training, mostly satellite applications. That's why we're going to talk a little bit, not only about the ENSO itself and the ENSO system, what it is, how do we monitor it, and but also a little bit about the satellite tools that we could use and that go into the monitoring of ENSO. So I'm Jose Manuel Galvez. I'm from Peru, but I've been in working here at NOAA for the last 12 years. And Bonnie?
Yeah, my name, like I said, I'm Bonnie Acosta. I'm also from El Salvador, but I grew up here in the United States. And I started working with the international desks Halloween 2022. And yeah, I've been learning a lot since then. We both have our backgrounds in meteorology as well, so it's been a lot of fun putting in all that we've learned in the classroom and applying it to real world applications. So like I said, we're really excited to be here, and again, thank you. And I'm going to reiterate what Jose mentioned, and thanking everyone for your attendance and for your interest in what we're going to be presenting.
All right, if you're, before continuing, we just want to give kudos and thank you to Karimar Ledesma. She's not here with us right now, but she's another member of our team, and she helped us a lot to put this presentation together. So without wanting to delay this more, let's get into this. So why are satellite tools so important for ENSO monitoring? And the reason is that satellite tools are key because they have high resolution in space and time. So this way we are allowed to measure remote locations that there would be very hard to measure if we're only using land-based or ocean-based instruments. And also we can produce data that have very high temporal resolution. So we have two types of satellites. We have the geostationary satellites and we have the polar orbiters. The geostationary satellites are great because they're constantly measured in a location with high temporal resolution. So we can obtain a lot of very quick updates with low latency. Low latency means that we can receive new information very quickly, so we can make a decision on the measurement or what's going on very quickly before it's too late. Then one of the limitations with geostationary satellites is that they are really high and really far away from the surface. I would say it's approximately 36,000 kilometers above the ground. Therefore, it's a little bit more complex to be able to obtain high resolution data no, for certain processes when we really want to go find resolution. Also, there it's very challenging to be able to place a microwave sensor, microwave data in the spectrum of the microwave, very long waves. Can penetrate clouds, for example. So we can, whenever we have a lot of clouds and possibly precipitation, the geostationary satellite cannot see through those clouds, but the microwave data that can be measured by some of the polar satellites, it can penetrate to the clouds and retrieve information. The limitation with polar orbiters is that because of the way they orbit the Earth, they only pass a very few times over a given location. Therefore, sometimes whenever you really need the data for the polar orbiter in one location, it's not available. That's why whenever you're using polar orbiter data, you actually look at constellations of satellites, and there are a lot of agreements between nations and institutions across the globe to share satellite data, so we can all benefit from that information. So this is the key advantage. We can obtain this high temporal and high resolution data, and you're going to see it a lot during the presentation, combining different data sets. Now, the disadvantage from satellite data are that sometimes there are potential biases in comparison with in situ observations, and you need to know those biases so you know how to interpret this data better. One thing I can think of just from the top of my mind, if you think about precipitable water, which describes the amount of water vapor in an atmospheric column, if you look at different satellite databases, databases that are derived using different satellite data, one of them that comes to mind is the MIMIC, total precipitable water, which we have been using for a very long time. And MIMIC is great, but in tropical continental regions, it can have a positive bias. It can be, so sometimes when you're looking at what the MIMIC is saying, you need to keep in mind that if you're in the Amazon basin, for example, or I know there's some people from Africa here, if you're in the Congo River basin or Southeast Asia, if you are inside Thailand or Cambodia or Laos, for example, your MIMIC TPW could be overestimating. So you need to keep these biases in mind. Also, as I mentioned before, if you're looking into some of the derivations that are more complex, for example, if you want to retrieve information that is happening underneath clouds, the satellites are also not perfect. Even when you can have these microwave sensors that can penetrate the clouds, sometimes you cannot get the information back. For example, you have a tropical cyclone going on or some other system that is producing very heavy rainfall, very large drops, then sometimes the microwave it cannot come back to the satellite, so you cannot measure through those clouds. So there are some disadvantages as well. So it's good to always use satellite data combined with other data as well. I know I'm spending a lot in just one slide, but it's very important to keep in mind that numerical models are great and they're getting better and better. They still fail a lot of times, but they help us a lot with the weather forecasting, right? And if you think about this, 85% of the data that goes into numerical models so they can run and produce a weather forecast, 85% of this data comes from satellites, mostly from polar orbiting satellites and some from geostationary as well. So that's a key number to keep in mind. And if you think about this, if we didn't have the satellite data ingested in the models, the forecast would be terrible. So really, satellite data has a very important impact in our way to sample the atmosphere and the oceans and the whole land, atmosphere, ocean system, and not only directly, just by looking at things quickly, but also indirectly by combining data sets and also by using numerical models, right? So this is the group that is conducting the SATMOC training. I'm not going to go into details for the sake of time. If you don't know or if you don't remember, we have 4 presentations. These are the dates that we're having these presentations. So today we are going to talk about the ENSO monitoring with satellite tools. Then we have a presentation and training on flood monitoring on June 25th. The next one is artificial intelligence applications on June 27th, and then drought monitoring in July 16th, all right? Therefore, we're gonna touch a little bit on the impacts of El Nino or La Nina, the ENSO system, on floods and also on droughts, since it's gonna be relevant to other, to future presentations coming up during this 4-session training. All right, so the outline for today's presentation is the following. The current session will focus mostly on a general overview of, we'll start with a general overview of El Nino Southern Oscillation, so main concepts, and then we're going to speak about a little bit about the teleconnection, regional trends and effects, including droughts and flooding, to talk a little bit about the impacts that the ENSO system can have. Then we're going to talk a little bit about the satellite tools, different satellite tools that we can use to monitor ENSO, which includes a little bit of a description of the tool and access and application methods for this tool. That being said, this is probably going to be on the second in the next hour, because we have a lot to talk about before we get to these tools. I also wanted to highlight the fact that when you think about the monitoring of ENSO, a lot of the tools that we use are a combination of information from different satellites and different algorithms. So it's hard to say, okay, this one satellite from this one a sensor measures this. Not really. So we're going to talk maybe a little bit about some of the sensors, some of the type of data that we're getting of satellites, but mostly we're going to talk about the tools that we're using, the final or the end and the end tool for the user to monitor the evolution of ENSO. All right. And finally, we're going to have a couple of exercises. And then again, this is very interactive, where we're going to talk about how to evaluate certain satellite products and tools that we're going to talk about during the session. So everyone as a group can help us discuss what might happen with the ENSO system after looking at that tool. Do you mind talking about this?
So, and I just wanted to add too that we'll be taking breaks in between. So every about 50 minutes or so, we'll be taking breaks, and we'll let you know. So again, we are the WPC International Desk at NOAA's Weather Prediction Center. We have been running since 1988. We are a NOAA WMO training program on weather analysis and forecasting to support capacity building in National Weather Service all over the Americas. So we primarily, like Jose mentioned, we primarily work with the Americas. But in the past, we have had other visitors that have come from other regions of the world as well. So our mission is to enhance forecasting practices, and we do that by providing on-site training to forecasters from the institutions of the Americas, and we divide them into tropical desk and South American desk. We conduct workshops and virtual training sessions such as these to provide more information and to continue fostering the learning of from different regions and continue the development of forecasting practices. We provide IDSS before and during extreme events, including tropical cyclone emergencies. So impact-based decision services for extreme rainfall events. So those are the things that we mostly focus on is precipitation. And we also develop and facilitate forecasting tools. So research to operations on our website, which is at the top right. You'll see that there are a few algorithms or forecasting tools that have been developed at the desks with the help of the trainees that have passed along throughout the years. They focus on severe weather, they focus on convection, just for a few examples. And with all of these kinds of interactions that we have with so many different services in the region, we strengthen ties in the international weather community. So we have a lot of discussions, we interact, we coordinate with a lot of the different weather services. So there's a lot of back and forth in trying to strengthen the ties and learn from each other. Additionally, with the same practices that we have, we also collect feedback from our partners to improve the U.S. National Weather Services, such as numerical weather prediction and satellite data as well. So want to
Yeah, and what makes a workshop great, right? What makes a workshop spectacular? And we need to always remember this when we are starting our trainings. What makes a workshop great is considering it as an open shared discussion where anyone can contribute equally. So we want to encourage you to please let's converse, ask questions, write things on the chat, because every comment is a contribution. In geoscience, there are no rights and wrongs. We are far from knowing 100% of the reality, and we probably never will. So there is not such thing as a bad or necessary question or comment. So just feel free to say whatever you want to say, because that's going to come to use for us. So the more we share and discuss, the more we learn as a group. This is very important to keep in mind. So let's keep going with this. I want to start. Let's start with the main presentation, right? It's already what, 25 minutes past the hour. Okay, so we're going to start talking about what is El Nino Southern Oscillation, and we're going to emphasize some on the global impacts because that's going to open the topic for future presentations on droughts and flooding. So El Nino Southern Oscillation, or ENSO, is the dominant interannual variability of the Earth's climate system. So among the different things that control how the Earth varies, we have the Antarctic Oscillation, we have the North American Oscillation, we have tropical waves, upper troughs, fronts, the polar vortex, blah, blah, blah. The ENSO is the main one, the one that has a stronger impact globally. So what is it? It is an oscillation of warming. The warming phase is called El Nino, and cooling, the cooling phase is called La Nina, changes in the sea surface temperatures in the central and eastern tropical Pacific Ocean, which also associate with changes in atmospheric circulations and the climate, right? So these changes that last several months in a large region of the ocean end up having an impact in the atmosphere, and then those impacts in the atmosphere can generate impactful weather events in different parts of the world. So whenever we're speaking about normal conditions means that the equatorial Pacific is mostly close to average. The temperatures and the flow is kind of, if you average a lot of years, a lot of months, you're actually closer to what you would have in the average, right? That's what normal condition means. So if we look at normal conditions, the Pacific Ocean has usually a warm pool. Red means warm. In this case, the colors are sea surface temperatures. So you have warm surface temperatures in the central and western Pacific, and then cooler temperatures in the eastern Pacific. Then the surface winds are from the east. You see these white arrows. These are showing this. This is a conceptual model, right? They are representing the surface winds, right? So what is happening? What is happening is that the water that comes into the South American coast and is coming from the south, right? Same happens in California, but that water goes offshore very, very far to the north from equatorial locations. However, the current in the South America, because of the shape of the South American coast and the Humboldt current, which is the current that brings cold water from the south along Chile and Peru and into Ecuador and the equatorial Pacific, because of the strength of the current, the shape of the coast, and other factors, these cold waters enter equatorial locations. Once you get to the equator, the surface winds, they rotate. They are mostly from the east, and these easterly winds, they push the currents and help to push these cold waters westward along the equator, right? Something else that happens in the equator is a little bit complex to explain, is that you have equatorial upwelling. I'm going to get to there a little bit later. So dynamical processes along the equator that have to do with the change of latitude, right? Those dynamical processes stimulate rising motion inside the ocean waters, or upwelling, and that upwelling can generate an additional cooling in the equatorial Pacific. So for many reasons, the equatorial Pacific is normally cool. The temperatures are cool. If you're in the Galapagos Islands in Ecuador, and you go to swim, actually sometimes the ocean will feel a little bit cool. However, if you are, say, in Papua New Guinea, and you go to swim, the waters are going to be really warm. So what is happening? These waters that come from the south and the South American coast and further north, they come from the coast of California and go into equatorial regions of the Pacific. Once they encounter this easterly wind regime in equatorial locations, the easterly winds will tend to push these waters westward. So what happens if you think about the water, a piece of water is located in the Galapagos Island, no, between this location and once it gets to Papua New Guinea, that takes a long time, and that's going to be exposed to solar radiation in the equator. So you get a lot of sunlight over a long period of time, so that helps to warm that water. And whenever we get into the Western Pacific, the water is really warm. On top of that, since the easterly winds are pushing the currents westward, we're also building a deeper layer of warmer water. So in normal conditions, you have cooler temperatures along the South American coast and a very shallow warm layer. And once you go to the west, in the Western Pacific, you have very warm temperatures. And very warm, I mean 30 to 32 Celsius, right? This is warm for the ocean. And also the layer, that warm layer can be really deep. Deep meaning the warm layer can go all the way down to 200, 300 meters sometimes. So it's a really warm layer. Now, once you think about equatorial upwelling in the Western Pacific, if you try to bring water up from the lower levels, that water is already going to be warm. So the impacts of equatorial upwelling in the Western Pacific are not significant. So you really get really warm surface temperatures in the Western Pacific. We're talking about the ocean. So if you think about the atmosphere also reacts upon what the ocean does. So in the Western Pacific, once you're warming up the surface, you will tend to lower the surface pressures, right? So that connects with what happens with the rest of the atmosphere, and you tend to enhance rising motion over the Western Pacific and maritime continent. Maritime continent meaning Indonesia, Papua New Guinea, the Philippines, no, Eastern Asia, basically equatorial Eastern Asia. So there's a lot of deep convection and thunderstorms and heavy rainfall occurring in this region, right? So this is kind of the normal conditions. Of course, there's day-to-day variability, but this is a rainy location. But what happens if you look at the vertical circulation, this region of rising motion, once it reaches the top of the atmosphere of the troposphere, which is called the tropopause, which is a very stable layer that is located, a little bit above the level where the planes fly, right? That's a very stable layer, so that rising motion cannot keep going. It has to spread horizontally. So what happens? You end up having this dominant westerly winds across most of the Pacific, and then you have a sinking branch that establishes over the western coast of South America and the Eastern Pacific. When you have sinking air in the atmosphere, that tends to limit the development of rain-producing clouds, and you tend to favor drier conditions. That's one of the reasons why the Galapagos Island and for example, generally the Eastern Pacific is less rainy than the Western Pacific. Even the coast of Ecuador and Peru are drier than if you live in Papua New Guinea, Northern Australia, or the Philippines, for example. Those are normal conditions. Now, let's start with La Nina, because La Nina is easier to explain before El Nino. When you're talking about La Nina, which is on the right, La Nina is basically an exacerbation of normal conditions. So what does that mean, exacerbation or enhancement of normal conditions? It means that your easterly winds over the surface of the ocean are going to be more pronounced. So you get stronger easterly winds, right? It means that the cold water along the South American coast and into the equatorial upwelling cold tongue is going to be more pronounced. So you get colder water. It means that the warm layer in the Western Pacific is going to be more pronounced, not only in terms of temperature anomalies, but it's going to be deeper as well. It means that the convection in Indonesia is going to be stronger, and the subsidence or descending air of the coast of South America is going to be stronger. So you're basically making this system stronger. The normal conditions become much stronger, right? This is easier to explain. El Nino is a little bit more complicated to explain. So El Nino means that actually you break the system and a lot of things change. So during El Nino conditions, the winds sometimes reverse. In the Eastern Pacific, this doesn't happen that often, so this graphic is probably not as accurate. So you still get a little bit of easterlies, but they're weaker, and sometimes you get some westerlies. But in the Western Pacific, you get these westerly wind bursts. Then the SSTs, the process is complex, and we're going to talk about it later. But the SST distribution or sea surface temperature distribution also changes. So you end up getting warm temperature anomalies in the Central and Eastern Pacific, and then the warmest waters, the 30 to 32 Celsius waters, they end up organizing in the Central Equatorial Pacific. So what does that do in the atmosphere? What that what that does is that enhances rising motion in the central Pacific, and it starts enhancing sinking motion or drier conditions in the maritime continents. So whenever you have an El Nino, those drier conditions over Papua New Guinea, Indonesia, Northern Australia, and Southeast Asia become more pronounced, and you tend to favor droughts, you tend to favor wildfires, and so on. So that's one of the reasons why El Nino tends to impact Australia and the maritime continent, Southeast Asia with drier conditions, and also India as well. The Indian monsoon also can be sensitive to El Nino conditions, and you could get less rain during El Nino conditions. We have a lot to say, but I want to do a quick check in case there's a comment or any questions on the chat, and please let me know. Okay, I see a question saying how it changes the Walker circulation. We're going to get to the Walker circulations in a second, but yes, this is the Walker circulation, Sudakar, and you can see that El Nino modifies these branches of the Walker circulation, right? The Walker circulation is the zonal circulation, or the circulation along the equator, and we're speaking about if you do a cross section of the atmosphere along the equator and average over a long period of time, you're going to see that what we were talking about before. We're going to see that over the maritime continent, you tend to have this persistent or dominant ascent, that in the Eastern Pacific, the dominant descent, and so on. Is there anything else on the chat that I'm missing?
There are a couple of new questions. One from Daniel. How do we relate these events with the conditions in the Greater Horn of Africa?
That is a very good question. I am not extremely familiar with the conditions in the Greater Horn of Africa, but we'll get to the slide of the impacts later. So let's just go very quickly to those slides. And these are El Nino climate impacts, and these are average. We're going to get to this in a second. So not all El Ninos have the same impacts. Not all La Niñas have the same impacts. We're going to get to that as well, because the El Nino system is also interacting with other stuff, other oscillations that are going on. They're interacting with, say, the PDO, the Pacific Decadal Oscillation, the NAO, the North Atlantic Oscillation. They're interacting with other SST anomalies that are inducing other features. So this is complex, but in general, if you look at a lot of El Ninos, this is what tends to happen, right? So if we're thinking about El Nino and you're looking at Eastern Africa, the Horn of Africa, from what I'm seeing right now, the impacts in that region are not as significant, meaning that the signal of El Nino is not as intense there. However, once you go further west, right, into Eastern Africa, this would be Tanzania, Uganda, Eastern Congo, right, Kenya. You can have a signal with El Nino. In this case, if you're between December and February, and you have an El Nino, you will tend to get wetter conditions in equatorial Eastern Africa, right? However, in Southeast Africa, this will be Mozambique, South Africa, Madagascar, Zimbabwe, Botswana, and Zambia. You will actually get drier conditions during December, February. But look at June, August. In June, August, the impacts are not significant in Africa. So seasonality on the impacts matters. You're not going to get the same impact during the entire year. They're going to change. Now, going back to this question, because we're stimulating discussion, right? Look at La Nina. La Nina is different. So first, look at June, August. I'm going to start with that. You could say, okay, in June, August, you have El Nino, nothing happens in Africa, so during La Nina it's the same. No, during La Nina, in June, August, you actually have an impact in West Africa. If you look at this, La Nina, during a La Nina, you tend to have cooler conditions, more cloudy conditions in West Africa. So actually, this happens all year round. So the impacts vary upon seasonality and upon location. Going back to the initial question, we already covered this slide partially, right? But going back to the initial question, I don't see a significant impact in the Horn of Africa region itself, which is like Somalia, Ethiopia, and and Eritrea, right? Any more questions?
There are a couple of questions in the Q&A session. Start with this one.
Oh, I see it.
Yeah, do you see those?
Why does the oscillation occur? Is there a bigger system that conditions its occurrence? Well, you know, that is a question that in reality, to answer it properly will probably take like a couple of days to do it properly, but we're going to touch into that because we need to speak about different aspects about El Nino to be able to explain. We're going to get to that. And I'm looking to the next question, Megan, which says, is there information about cold Kelvin waves associated to the Nino event? I don't know if there's an updated online resource, particularly speaking about those or a new papers. I need to be updated myself, but I'm going to talk about it. So we're going to talk about that. Megan, do you? Oh, I see. Okay. Anything else, Megan?
I think there's also a lot of questions that have to do pertaining with certain areas. So maybe we'll probably be, discussing those regions as well. So we can probably also continue because I feel like there's a lot of questions that they'll be answered later on too. So
okay, great. And please, well, Megan is on top of everything, but Bonnie here as well. Please let me know.
I'm trying to keep track.
Yeah, let me know if you see something that I'm missing or that you think it might be relevant, and please stop me because it's hard for me to look at the chat while we're presenting. But thank you so much. We'll keep going then. Okay, let me go back to the previous slides. And as you see, I'm taking a long time to present, but we're gonna get there. All right. So we're talking about this, the three phases of El Nino. This is the same thing, but looking at it differently. So normal or neutral, this is what we have. Then El Nino is when everything changes and everything changes location, and then La Nina is an exacerbation of neutral conditions. So this is a summary of the three main phases of El Nino. Now, why the name? And I'm going to try to make this short. This is for general reference to see why El Nino Southern Oscillation is a very complicated name. Well, El Nino means the child. What? And Southern Oscillation is why Southern if it's in the equator. Okay, so there are two terms that eventually merged. First, we have El Nino concept, and El Nino concept is earlier than the Southern Oscillation. The El Nino concept came from actually Peruvian fishermen, well, Peruvian, Ecuadorian. At that time, it was all the viceroyalty of Peru, part of Spain, right? And Peruvian fishermen, they were eventually trained to be Catholic, right? They had a different religion before the Spanish came. They became Catholic and they started celebrating Christmas, right? And they started using the term El Nino current to this warming of the ocean that usually started around Christmas. And El Nino comes from El Niño Jesús in Spanish, which means Jesus the child. So El Nino is child, right? It comes from Christmas, and from Catholicism. The El Nino, where's El Nino comes from that. So what happens that the fishermen, they already knew from ancient times before they had this name that occasionally in some years, this warm current was extreme. The ocean really warmed up and they started getting pouring rains and the fisheries changed and they get a lot of scallops and shrimp, what they usually didn't get as much. So they realized, okay, they started calling that El Nino phenomena. So when in South America, the term fenómeno del Niño or Niño phenomenon is very much used associated with El Nino events, what now we call El Nino from the global NOAA and world perspective, right? Now, that was happening a long time ago, since the 1600s. Now, in Asia, now we're going to go to the other end of the world. In Asia, India is much more populated than South America is. So there's been a lot more people much far away in time, right? So impacts of the weather and climate in India were significant. So in 1887, there was a severe drought. The Indian monsoon, which happens this time of the year, actually between June, July, August, and September, the Indian monsoon didn't produce much rain, and there were a lot of impacts. And then in 1888, once again, a lot of impacts. So researchers started saying, okay, no, what's going on? We need to try to find out how to forecast this because this is affecting a lot of people. So that prompted research. There were a lot of researchers looking into this, but the one that put kind of the pieces together and gave it a name was Sir Gilbert Walker. I don't have the right date. I think it was in the early 1900s, if I'm not wrong, but he called it the Southern Oscillation because he realized that whenever there were droughts in India that was related to a change of pressures between Australia and the Southern Pacific. That's why the Southern Oscillation, because the stations that showed this seesaw difference in pressures were both located in the South Hemisphere. One of them is Darwin, located in Northwest Australia, and the other is Tahiti, that was located, it is located in French Polynesia in the center of the South Pacific. So the signal of this oscillation was happening mostly in the South Hemisphere, but close to the equator, and the big impacts were in India. So anyway, they call it Southern Oscillation. And then eventually they started realizing, when there's a drought in India, there's also a drought in Australia and in Indonesia. And so they started making connections, but they weren't linked with El Nino until the 1960s. It was in the 1960s when Jacob Bjerknes, this is the second Bjerknes. The first one was Wilhelm Bjerknes. This is the second Bjerknes. He made the link of El Nino and the Southern Oscillation are linked somehow. And after that, everyone started realizing that the satellite era came and they realized, okay, yeah, there's something there. They are linked somehow. So that's where the name came from different aspects around different parts of the globe that eventually made sense once we started getting better data and understanding the whole global atmosphere and ocean and realizing, oh, these are linked together. That being said, not always when we get a certain southern oscillation, we get an El Nino and vice versa. So they are linked, but they don't always work together. So there's complexity to that. ENSO monitoring. So ENSO is very complex. This can be monitored in a different way. So there are a lot of variables that we look, but to make it a little bit more simple and consistent, the way this monitored right now, at least officially according to NOAA, is by looking at these 4 different areas in the ocean, in the equatorial Pacific. You can see them here on the right. You have, first there were 3 regions designed, Nino 1+2, and this came from the early 1980s after the 1982-83 El Nino. Which was devastating for Peru and Ecuador. So we have Nino 1+2, then you have Nino 4, Nino 3, and Nino 4. Now, once scientists started realizing, well, we really need to understand this and forecast it because the impacts are really bad and around the entire globe, they realized that the region that affected mostly, that had the strongest impact in the United States was Nino 3.4. So it was something in the middle between Nino 4 and Nino 3. So this region, Nino 3.4, was created. And they also realized that forecasting El Nino was better if we use data from the 3.4 region instead of 4 or 3. So that's why El Nino is being monitored mostly with sea surface temperature anomalies in Nino 3.4. In order to classify it, you need to verify that the event is going to be persistent. So if you get a little warming, you can call it, oh, do we have an El Nino, right? No, you need to make sure that that warming is going to persist for a period of time, that is going to be extended over an area, and it is associated with other factors. So that's why to call it El Nino or La Nina, you need to wait for 3 consecutive trimesters of an anomaly. Well, the threshold is 0.5 degrees Celsius. So you need to wait for 3 consecutive trimesters with that anomaly. So that is great in the sense that it builds confidence on that you are actually going through some consistent event, right? That you can say, okay, yes, this is persistent. The one thing that you need to keep in mind is that the impacts in the atmosphere and in other parts of the world could start as soon as the ocean looks like an El Nino or a La Nina. So if you're saying, okay, I'm going to wait until this is officially declared, then you're probably going to have a lot of people already underwater or suffering droughts and wildfires and other impacts. So This is it's not that the classification is wrong. I'm never going to say that. You just need to have clear that you need to, as a forecaster, especially if you're looking into impacts, you need to be monitoring all the time. So as soon as there's warning that, well, we might be going into an El Nino or a La Nina, and as soon as you see that the ocean surface temperature is starting to behave a little bit like that, you need to watch out for impacts because they're going to start happening then, not when it's declared officially. Something to keep in mind.
So really quickly, there was a question. Can you
Go ahead.
explain that? It's very relevant, I think. Can you explain what is 3.4? So El Nino 3.4.
Yes, El Nino 3.4, it's this region located in the equatorial Pacific that is between, this would be, well, this is 120, and this would be one, I should have, I should have the number handy, but I forgot it. I think it's 170. So it's a region in the equatorial Pacific that has variability in the temperature of the ocean that links to the identification of El Nino events. So whenever you get after doing statistical analysis, researchers doing statistical analysis with sea surface temperature databases over a long period of time, they realize that the variability of the sea surface temperature in that region really correlates well with the occurrence of an El Nino and an El Nino with impacts in the United States. So in order to gain confidence that an El Nino event is happening, scientists like looking at that particular region because that will help you to gain confidence in saying, yes, an El Nino or a La Nina is present. That's why they monitor Nino 3.4. And yes, before we keep going with the slide, I think, yeah, we're about, it's probably a good time to take a little break to stretch our legs or bio break. So it's in the Eastern United States right now. It's 1:52 p.m. Would, Megan, would you be okay if we take a break until 2 p.m. sharp?
Sure, not a problem. I would advise that nobody leave the Zoom since we are at capacity. This is a technical issue I'm still working through because we've not ever hit capacity before. So
Yeah, wonderful. Thank you. Yeah, please don't leave the Zoom. Okay, so see you at 2 p.m. sharp. Keep going. Okay, great. We're recording, so let's keep going. Any else? There's a lot of information in the chat. So I don't know if there's something I should address.
So right now there's a question. Can you please touch on the ITZC role, influence, and relationship with Southern Oscillations? Thank you.
Okay, and okay, that's a great question, as many of those are. So let me do something. Let me get out of the presentation for a second. We're gonna go into the ITCC. So what better way than looking at the current situation right now? Oh, I just realized I have to see anyway. All right, so 1 second. Okay, so this is the current situation where we're in the Americas. We can change to other parts of the world. So I'm going to start with the Americas, and then we can look at other satellites. We have Himawari for the Western Pacific, and also we have Meteosat for the Indian Ocean. So let me do something. This color that I'm showing is called the geocolor. So it's an image, it's called a true color image. So this is something that we would see if we were on a spaceship or on the satellite, right? Our eyes would see something like this. So in this image, for our eyes, clouds usually look white. So we can have an idea of where the cloud systems are. So in this particular case, I'm gonna use pink to draw. This is the ITCC, and this right now in the Americas. Well, there's an event going on right now, which is called the Central American Gyre. So this is a different thing. We can speak about ENSO though and Central American gyres briefly because actually whenever you have a La Nina and a developing La Nina this time of the year, this tends to stimulate the generation of Central American gyres, which are these large scale rotation systems. And you can see there is some cyclonic rotation right now in the Gulf of Mexico. So what this does, since you have this unusual area of lower pressures, this will draw the ITCC to the north, and the intertropical convergence zone is very likely doing this. And in the Atlantic is actually less it's more closer to what there should be. So yes, the ENSO can modulate the ITCC, but it would also depend on the synoptic situation. So in this particular case, the ITCC is very well displaced to the north. Why? How can the ENSO affect the ITCC? One of the direct mechanisms is that ENSO relates to equatorial temperatures. So if we have cold SSTs or colder than average, which is what we have right now in the Eastern Pacific, then the warmer sea surface temperatures are gonna organize further north. And what's gonna happen? What's gonna happen is that the pressures in the lower levels, they become lower. Generally, they will tend to be lower where you have the warmer surface temperatures, right? So the ITCC, Intertropical Convergence Zone, also called monsoon troughs, depending where you are, will tend to go towards the warmer sea surface temperatures. So whenever you have a La Nina, in this time of the year, when the ITCC is north of the equator, the ITCC is going to try to go further north. When you have an El Nino, it's the opposite. When you have an El Nino in the Eastern Pacific, since you got the warm portion, I'm going to draw an El Nino is going to be red. Okay. When you have an El Nino, then actually the tropical or equatorial Eastern Pacific is warm. So the ITCC is going to trend further south, and it's going to go closer to the warmer water. So let's do something here, and let's switch to the Eastern Hemisphere. And you can do this here. Let's pick the satellite. So let's go to Mediasat East. Might need to reload. There we go. Well, it's nighttime, right? In a lot of the Eastern Hemisphere right now. I'm gonna change the product. We have this is called the geocolor at night, but there are other products that could show what's going on a little bit better. So let me change this for a second. Oh, okay. Hold on one second. This is taking a while to load, so I'm gonna use another band. 10.8 micrometer. There you go. All right. Okay, so we're in the Indian Ocean and we're in Africa right now. And what we can see is, I'm going to draw the ITCC. So in West Africa, this is probably a tropical wave. In West Africa, the ITCC is already over the continent. And then once the ITCC entered the continent, in some places it's called net near equatorial trough or sometimes monsoon trough. So to me, it looks like it's somewhere here, right? But now, once we look into the Indian Ocean, to me, the ITCC is maybe somewhere here, and I wouldn't know what to do further east. So whenever you have a La Nina, whenever you have a La Nina, like right now, we're having a La Nina developing, right? It's not there yet, but it's trying to develop. You tend to exacerbate the Indian monsoon, and so that would tend to draw the ITCC further north. Whenever you have an El Nino, that's the opposite. So it really depends where in the world you are, and in some cases you will not get an effect from El Nino into the ITCC. Will. Okay, all right, let's move to the next one. It's always very little time to address all the questions. Anything that, I know there's a lot of great questions, but let's pick a couple before we keep going.
Someone was asking to explain El Niño Costero.
Oh, wow. Okay. Yes. All right. How do we do this? Let's go back to the presentation maybe, because we have, and actually I have a page, before we go to the presentation, I have a page here open This is one of the many pages available. This is the NOAA and NVL, and we'll pass you the presentation after as well. So don't worry about not having the links available. But this is actually a website organized by NOAA to look at different data, and I have it here right now. So we're looking at the SST anomalies. So let me go to 2023. Well, let's go to 2017 because there was a Nino Costero in 2017, right? Okay, so this is the 2016 El Nino. So this is the end of it. But if you look at the South American coast, it wasn't that warm. It was really not that warm yet. However, if you keep going forward, you can see this is April. Once you got into April or May, you can see the La Nina developing, right? Or neutral conditions, but you know, you get the cold tongue in the Pacific. And look at what happens. September, I'll stop in November, cooling in the Pacific, and there's a little bit of warming in the Peruvian coast and northern Chilean coast. But look what happened in January. In January, you had this sudden warming along the coast. And this stayed. Now we're in February. Now we're in March. Look at this. Now we're in April. So you have this very pronounced warming. But if you look at the warming is only along the South American coast, but it's not really over the western, central and western Pacific. So El Nino Costero is a warming that occurs only along the South American coast. Costero means coastal in coastal El Nino, and it warms up the regions Nino 1 plus 2. So what causes the coastal warming is very complex. So for the coastal warming to develop, you need local processes that happen along the South American coast that are not in phase with the rest of the processes that induced the ENSO system. The rest of the processes for the ENSO system, you get the sudden oscillation, you get the westerly windwards over the surface of the ocean, and so on. So those are not there. But there are local processes along the South American coast that generate a warming that only stays along the coast. So that is El Nino Costero. Sometimes these El Nino Costeros can evolve into a basin El Nino. This is what happened last year in the 2023 one. But sometimes this El Nino Costero only constrained to Peru and Ecuador. So this is a very short explanation because this is a very complex topic. Anything else that I should? One more question. And we can start drifting towards the presentation while Bonnie finds the question, or Megan.
Well, basically the question was there any kind of interaction, or what was the connection between El Nino or ENSO with the IOD in the Indian Ocean?
I will need to read more about that. The IOD is the Indian Ocean Dipole. I will need to read a little bit more about that. But the IOD actually does affect the African Horn that we were mentioning, like Somalia, Ethiopia. It does affect the African Horn, but I don't know the connection between that and El Nino. So that's a question I cannot answer at this time. But write it down. All right, next. To keep going with the presentation. All right.
Well, I have a question.
Go ahead.
Like the La Nina is specific to only South American countries, or it is over the Indian Oceans also?
Well, both El Nino and La Nina, they mostly form over the Pacific, but the impacts can be global. That being said, let me find the slides where I have the impacts. We were talking about the monitoring. So we'll go back to that. Yeah, ENSO impacts, right? And I had this slide before the impact saying, but why do we care so much about El Nino and ENSO, right? Could be El Nino and La Nina. It's because the impacts are global. So as you saw before in these graphics, most of the warming occurs in the Pacific, right? And most of the atmospheric changes occur in the Pacific, but they are connected with other parts of the world. So if you look at climate impacts, you can see that, well, you asked about La Nina, right? You can see La Nina, the impacts of La Nina are actually all the way around the globe. So where are you located?
Located in Europe, in the central part of Europe. So
Central part of where, sorry?
central part of Europe.
Oh,
So
Europe.
we're not
Okay, Central
far
Europe.
apart. Mhm.
All right. So if you look at least at the main impacts from El Nino and La Nina, for example, in Europe, they're not as significant, right? In
Yes,
Europe,
okay.
it's probably reacting to other types of oscillation. So even
Mhm.
December, February, and June, they're not as significant. But you see that, for example, in northern Canada, once you have an El Nino winter, you tend to have much warmer conditions. So
Yeah.
so it depends where you are. So the impacts can be global. And why do we get these global impacts? Is because of what we call the teleconnection. So I'm going to find the slide. Yeah. And this is what we call teleconnection. So a teleconnection is a relationship between changes in regions that are really remote, but these connections are physically related, right? So you will think, why am I getting why am I getting, say, a warmer winter in Canada whenever I have an El Nino? See, El Nino is focused on the Pacific. So why am I getting this? And the reason is that the atmosphere in the Pacific is communicating with the atmosphere in Canada through different processes. So this is what we call a teleconnection. And that's why the rainfall in a very remote location is related to El Nino. This is just a slide that I won't have time to explain with detail, but this is already showing some of the different processes that could lead to a teleconnection from what is happening in one place with the other. So in this particular case, this one slide is showing that you have a lot of thunderstorms and deep convection occurring in the maritime continent. So what that enhances this thing that we call upper divergence. So basically the flow in the upper atmosphere opens up, and once you generate these thunderstorms, whenever you're thinking about the tropopause, which is in the top of a little bit above where the planes fly, right, the top of the troposphere, it's a stable layer, right? So when you have these thunderstorms, it's like you're punching the tropopause. You're hitting it, and that generates waves that propagate in the atmosphere. So that wave propagation can go really far and trigger weather in remote locations. Then other things that you have is you could get these thunderstorms. They can generate coolings and warmings, and those coolings and warmings in the upper atmosphere, they can change the circulations and change the way the systems move to remote locations. Then you have other things that are called atmospheric rivers, that are regions of high moisture content that are very elongated or long. So these could also change the weather in very remote locations. So there are different ways that cause that a region that is really remote can connect with a region that is really far away. So for example, the fact that you get a warm winter in Canada, you can actually get a warm winter in Canada with El Nino even when the tropical Pacific is not connected to Canada. So that's a teleconnection. So that's why El Nino is important, because the impacts occur globally, and sometimes these impacts can be very significant, and they can be also very persistent. Sometimes it's just very, very persistent. And that's a problem because, for example, if you have one rain event and then the rest of the time your weather is normal, then okay, you'll get a little bit of an impact. But whenever you have El Nino, you will tend to favor rain events in the same location for months. So you will get rain event after rain event, and then after the third rain event, your soil's already saturated. So the next rain event you get is still just going to flood, run off, and so on. So that's why El Nino is really important, because it tends to produce persistent impacts in the same location that can exacerbate, persistent weather events in the same location that can exacerbate the impacts.
One
There's a
more.
question
Thank
that's
you.
related. What is the dominant teleconnection source? Is it the Rossby wave source?
Depends. That's a very good question. It's more technical. It depends. It depends what it is. Rossby waves, yes. Rossby waves are waves that propagate in the troposphere and that can also modify, generate trains of waves that can modify the weather in remote locations. But there are other factors that affect. So it really depends. And since you're bringing that up, I'm gonna go down. So I'm just jumping through the presentation at this point because the questions are really good and they're just all relating to different material we have on the presentations. Let me go down and yeah, ocean coupling. And after ocean coupling, I have this other slide that is showing the heating that the ocean can induce in the troposphere. So this is another thing that also plays a role. So as an example, here we have a warm ocean, and apologies because this is in Spanish. But if you listen to me, you have a warm ocean, warmer than this area to the east, right? So this is cooler, and the one to the west is warmer. So the way the ocean communicates with the atmosphere is via fluxes, right? So in this case, the atmosphere is cooler than the ocean, so the fluxes are going to go up, and the ocean is going to warm up the atmosphere. In this case, in the east, the ocean is actually colder, so the atmosphere is going to warm up the ocean. The fluxes go in a different direction. But what happens over time? Over time, the atmosphere communicates, especially once you're in the warm region, you will tend to communicate with the rest of the atmosphere, and that warming that you're generating makes the column expand. This is physics. I mean, we won't go to the equation of state, but basically, the more you warm, you will tend to cause the column to expand. So the atmosphere bulges, right? And then the wind will push that warming downstream. So if we have a westerly wind over this warm anomaly over a period of time, this will tend to favor the development of in meteorology, we call these upper ridges, or these regions where the atmosphere is bulged downstream. And these regions of bulged atmosphere or a more compact atmosphere can also modify the winds. And those winds are going to modify also the weather. So it could be the Rossby waves, it could be these mechanisms, and a couple more. So depending on the situation, really, that's a question that doesn't really have a concise answer. It depends on the situation. And it's a very good question. Should we keep going then with the presentation? Okay. Well, where were we? Okay, well, we'll talk a little bit about ENSO monitoring, and let's just go really quickly. So one of the reasons why they're monitoring Nino 3.4 is the main way of monitoring ENSO is computational simplicity. It's also highly correlated with other variables like pressure, winds, and convection. And then given that this goes into satellite data, right? There's basically once you start looking at different data sets that are derived from satellite, among observations as well, because once you're looking at SSTs, you're using a lot of satellite data for the high resolution, high temporal and spatial, especially spatial resolution. But you're also considering other data. You have data from fixed buoys, from Argo floats, which is another type of buoy. You're getting data from just in situ temperature measurements from ships that are in the ocean. So all that goes into the database. But what happens? All databases are a little bit different to each other because of this, because they are approximations to reality, right? So the fact that sometimes when you're using different databases, you end up getting a different result. You know, it also kind of forces you to use a simple way to decide when you have an ENSO or not. So that's one of the reasons why they're also trying to simplify the classification of ENSO to this region and to particular data sets. And then the threshold for plus minus 1.5, it's user requested. So communication with the users, at some point they agreed that, okay, we're going to use this threshold to call it an El Nino or a La Nina. So there's a lot going on behind the classification. I wanted to touch about recurrence of El Nino, well, of the ENSO, El Nino, La Nina phases, and it oscillates, but there's not a well-defined periodicity to it. We have periods of time. For example, look at here between 1930 and almost 1940 and 1937, there was no La Niñas or no El Niños, at least according to the way that we classify them. So the system was quiet. It was all the time mostly close to normal, what we call normal or the average, right? But then look at the 1990s, and we're not showing intensity of events, but actually, in the 1990s, there were a lot of El Niños recurring one after the other. They weren't extreme until this one, but they were recurring El Niño, El Niño, El Niño, El Niño, right? Then look at here at the 1970s. 1970 was La Niña, La Niña, La Niña. And then sometimes you just go back and forth from one to the other. So the periodicity is not really defined. It's usually 2 to 7 years, but it varies. Okay, so let's go back into impacts. I know there's a lot of interest in ENSO impacts, and we're speaking right now about the 1998 El Nino. This was one of the stronger ones. And you can see, I don't have the scale. Well, the scale you cannot see very well, but basically the warming was very pronounced across the central and the eastern Pacific. And this stayed for at least a year. And you can see the impacts on precipitation. So this is the total rainfall. But these are the departures. So once you look at the anomaly of rainfall, the main anomalies were in the Central Pacific, right? So instead of having most of the heavy rainfall in Indonesia, actually the heavier precipitation was in the Central Pacific, but a lot of this anomalously heavy rainfall organizes over the anomalously warm water. So you can see positive rainfall anomalies all the way into the western coast of South America. And then you get, since we're talking about the Walker circulation, right, which is the equatorial circulation, since we're producing more ascent and rainfall over the equatorial Pacific, then you stimulate sinking motion or air that is coming down over the Amazon basin. The Amazon basin in South America is here. So it's raining a lot in northern Peru, in Ecuador, in southwest Colombia, but in areas to the east, you're getting very little rainfall, right? So that's related to it. This is a kind of a classical strong El Nino signature. But also you're enhancing sinking motion here. So another region where you enhance rising motion due to more complex processes is Southeast Brazil, Uruguay, Eastern Argentina, right? So some regions react with more rising motion, others with more sinking motion. On the other side, whenever you have a strong El Nino, you will get usually a very significant drought in the Philippines, in Indonesia, and then in parts of Northern Australia as well, and even Eastern Australia, right? And in this case, you can see California as well gets more precipitation around El Nino. So this is what is called a teleconnection. So for the fellows in this training, workshop, conversation that know a little bit more about, that have a deeper knowledge about meteorology, this could be a Rossby wave signature. You see positive rainfall, negative rainfall, and positive again. This could be a train of Rossby waves. Here, you could have another train of Rossby waves. So positive, negative, positive. So, but there's a lot of other things going on. Now, going to La Nina, the impact's a little bit different. So over the equatorial Pacific, this is the opposite signal. Now look that this is just one La Nina, right? We're just looking at one event. So the point that we wanted to make here is that the impacts are not going to be exactly the same with all the Niños and with all the Niñas. So in this case, instead of getting, you would expect that with La Nina, you're going to get very little rainfall in Ecuador and northern Peru, but in this case, they got a lot. So the impacts can differ between events. We've seen this before a couple of times because there's interest in impacts, and yeah, then again, just gonna talk about it briefly again. You can see that the impacts are global. Some areas will never find out. If you don't look at the news, you will never know there is an El Nino. For example, if you live in Sweden, in Norway, or Finland, it doesn't really matter if you have a Neo or Nino. The impacts are really, they don't feel them, right? But there are other parts of the world, for example, in Asia, if you're in Indonesia, in Northern Australia, in the Philippines, you really need to know, because the droughts and floods are highly sensitive to El Nino. So you really need to know to monitor and follow ENSO. All right, let's keep going. This is also to show some of the connections between the atmosphere and weather in remote locations. This is mostly for the US, this is a US perspective among many. And what you can see is that during La Nina, and this is mostly during the winter, during La Nina, because of these teleconnections, the Rossby waves, the way the upper flow reacts to warmings, right, and the circulations change, you tend to have something called the subtropical upper jet that goes further north. So the upper jets in the atmosphere are regions of very strong winds that are usually positioned in extratropical or subtropical locations, but really high up, right? So actually, some of the planes, to get faster from a location to another, they sometimes get close to the upper jets because they will save gasoline, right, from getting from one location to the other. But sometimes if the jet is too fast, you can get too much turbulence. So you need to know where to fly, right? The upper jets have a very important role in modulating the weather and climate in different locations. So whenever you have a La Nina, right? When you have a La Nina, the upper jet in the western United States goes to the north, right? And this is called the polar jet. So it's another jet that comes from the poles that actually digs into the Northeast United States. So what happens, I'm not going to go into details, but whenever you get this upper jet digging into the Northeast United States, you get a very cold winter in the Great Lakes region and in Eastern Canada. It gets really cold, right? But a lot of rainfall is associated with the jets. So actually you get very rainy conditions with La Nina. The rainy conditions are in parts of the Northwest United States. And since all the rain is further north, then the drier conditions as in the southern United States in winter, right? But when you get an El Nino, the upper jets change because of these teleconnections, and then you will get actually a strong subtropical jet really far south, and that will cause a lot of precipitation in the southern US, in northern Mexico, in Florida. So winters, when you have a strong El Nino, you tend to get a lot of rain in Florida, southern US, northern Caribbean, Cuba can get a lot of rain. And then since the polar jet goes further north, then your winters in Canada and the northern US are mild during El Nino usually. So we just wanted to show other aspects of the systems that can generate changes that are remote to the main source of the anomalies associated with El Nino. So the upper jets is a way of communicating also what happens in the Pacific with what happens in remote locations. All right. Any questions, or one or two questions maybe?
Yes, so there were a few questions about westerly wind bursts. What factors modulate the frequency and intensity of westerly wind bursts? How are they expected to behave in changing climate? As well as, does westerly wind bursts trigger the El Nino or La Nina, or El Nino La Nina cause westerly wind bursts?
This is a very good question. And since we're speaking about westerly wind bursts, I know we have a very diverse audience. We can be a challenge because it would be nice if everyone can follow this is a medium, it's kind of a technical question, right? Westerly wind bursts can trigger changes in the ocean surface and beyond the ocean surface that can actually develop an El Nino. I'm going to see if I can explain this quickly. I'll try. So what's going on is usually you have these are cross sections. These are trying to reflect cross sections, and so this is height or elevation on the y-axis, and on the x-axis we're looking at distance and east-west. So this is exaggerated. What happens that in the Pacific, as we mentioned before, the winds over the surface are mostly from the east, right? Those winds push the current, so you tend to have also a current from the east, a superficial current from the east, and then the ocean surface slopes gently towards the west. So towards the west, the ocean surface is higher. That's why altimetry data, which is only provided by satellites, is important, because with altimetry data, you can estimate the height of the surface and have an idea if how elevated your ocean surface is, and if you might have something called a Kelvin wave or not. We're going to talk about Kelvin waves in a second, right? So what happens if you suddenly produce a westerly wind burst near the surface? That is going to do a couple of things. First, it's going to crash with those easterly winds and generate probably a thunderstorm in the atmosphere, but that will also modify the surface currents, and that could actually enhance a westerly current that could produce, once it crashes with the easterly current, it will produce some sinking, right? So what happens? The longer that westerly burst over the ocean surface, the more significant the sinking. And this sinking can propagate. This is usually for this to happen, it tends to happen in the Western Pacific, a little bit west of the dateline, or 180 degrees, right? So we'll be in the Western Pacific. So the more significant this process, meaning the stronger the westerly wind bursts at the surface and the longer the duration of these westerly wind bursts, the more bulging you're going to cause inside the ocean surface. So your altimetry on polar satellites is going to say, ooh, sea level is higher, right? They're also going to say, oh, look at this. The thermocline, this is called the thermocline, is the region where where it's basically what separates the warm ocean surface layer with the cold water underneath, right? So the thermocline also bulges downwards, right? The satellite, question on the chat, do you think the satellite is going to be able to tell you if the thermocline is going down? Yes or no? And I guess we can get a couple of answers. The question is, do you think just with satellite data, you could tell, satellite data alone, I'm not talking about numerical models, that's indirect. Satellite data alone will be able to tell you if the thermocline is going down, or basically if the subsurface water it's becoming more profound, yes or no?
So we have a no, we have a yes.
Ooh.
We're getting more no's.
Well, then again, there's no right and wrong, right? Because if you consider that all the satellite data is going into numerical models, the answer is yes. Then
we're
if
just-
if you ignore numerical models, the answer is probably no, right? So yeah, good. See, there's no right and wrong. So I'm glad you guys are participating. Right? It depends what you're looking into. So actually, measure just with satellite data, you cannot really see too far below the ocean surface. So all that data is actually coming in directly to numerical modeling. The best data to measure these are buoys and that this is a complex topic, but anyway. Altimetry, though, you can measure directly with satellites, with polar satellites. They have, we have a couple of slides on altimeters later on, but actually altimeters will be able to tell you if your ocean surface is elevated or not. So in this particular case, you see that the time goes this way. So the next slide will be this one, and you can see that you start getting this recirculation in a bulge region of water that propagates eastward towards the South American coast. So that those westerly wind bursts tend to form in the Western Pacific, and then that bulging of the ocean, that like warm water with high surface and very deep thermocline that propagates towards the South American coast is called a downwelling Kelvin wave, or a warm Kelvin wave. Now, you could also get a cold Kelvin wave or an upwelling Kelvin wave. The process is the opposite, and we're going back to the question from before, from the last session. If you get actually a burst of strong easterlies over the surface, the opposite will happen, and you will actually tend to generate a cold Kelvin wave. All right. So what happens? The warm Kelvin wave will propagate towards the South American coast, and if it gets triggered along, 1 second, where am I? If it gets triggered along here, we'll say along 180 to 150 east, it will probably take 2 to 3 months to reach the South American coast, but under the surface. If you have an altimeter from a satellite, you could tell that there could be a Kelvin wave because you're going to see the bulge in the ocean surface moving towards the coast. If you don't have it, you won't be able to see it. But now we have a lot of great data. We have the altimeters, but it's also good to have buoys and other data so you can see what's happening underneath the surface, because you'll see the bulging, but you will also see the warm temperature anomalies propagating from west to east. And what we have here is an example of a potent Kelvin wave that is moving towards the South American coast. All right, so the question before about the westerly wind bursts, do you have it handy?
Yes.
I wanted to explain this before addressing the question.
Right. So there were two. It was what factors modulate the frequency and intensity of the westerly wind bursts, and do wind bursts trigger, or westerly wind bursts trigger ENSO, El Nino, La Nina?
That's a good question. And the second answer is yes, not always. But let me do something here. Before I do that, let me. Okay. Okay, so the second answer is yes. Westerly wind bursts can trigger El Nino, or they cannot. Sometimes they don't, because you need other factors to be in place. But that being said, yes, westerly wind bursts can trigger El Nino because what they do is they will tend to trigger this Kelvin waves. So this what I just shown, what we're showing here on the screen, and these Kelvin waves will move towards the South American coast, and once they get to the coast, they will upwell or reach the surface, and they can start generating the surface warming that eventually expands into El Nino. But in order for that to happen, you need to have other things in place. I mean, of course, it's important that your Kelvin wave is massive, like this one actually in the image. But for the sake of time, I'm not going to ask a question to the public. I was going to say, do you guys remember if this Kelvin wave triggered an El Nino? So I'm going to answer for the sake of time to my question. And no, this one didn't. And actually, everyone was worried because this looks massive. If you look at this constantly, you look at this and like, oh, this is serious. But the rest of the environment wasn't ready. There were other factors that weren't there. So not all Kelvin waves trigger El Nino, but they can. So yes, when you are forecasting El Nino, you need to monitor westerly wind bursts closely because they can. Then coming to the frequency of westerly wind bursts, and for this, I'm just going to show, let's look at satellite data. Or light data. And something that I like looking is, this is one of the many websites that are available. Personally, I'm a fan of this. I think Bonnie's too, if I'm right.
Yes, very much.
Okay, so this is one of the many websites. This is actually held. It's in North Carolina, so it's North Carolina Institute for Climate Studies, and Carl Schreck works there. It works a lot with trying to identify the Madden-Julian oscillation, atmospheric Kelvin waves, which are different than oceanic Kelvin waves. Right now, we've been talking about oceanic. The process is kind of analogous in a way, but Kelvin waves happen in the upper atmosphere, whereas the tropospheric Kelvin waves, whereas the El Nino Kelvin waves happen in the ocean, right? Anyway, in this page, Carl Schreck has an algorithm that tracks the potential occurrence of the Madden-Julian oscillation, tropospheric Kelvin waves, and other factors. Why? Because they impact the weather, and actually the Madden-Julian oscillation can trigger these westerly wind bursts that can trigger Kelvin waves. So something that we're going to look into, and I won't have time to explain this with detail, but let's do something. Let's look at archive. All right. So we were talking about the 2014, I think. Yeah. All right. 2014. While this loads, let me back to the presentation very quickly. So March 2014. So the westerly wind burst probably occurred in February 2014. So let me go to let's go February 20. Oops. Dun, 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 dun. The archive is different that for a long time. Okay, let me look at another event because I don't want to delay the conversation. Let me look at 2023. You're out of Zoom? Can you hear me? Okay, we're good.
Yes.
Okay. Okay. I thought we lost connection, but no, we didn't. Okay, let me look at 2023 and let's look at okay. There we go. Okay. Okay, I'm gonna talk about this very quickly because it will take me forever to explain this with detail. But whenever you see the green, this very dark green and also very dark brown, it means that something that is called the Madden-Julian oscillation, which is an oscillation that occurs globally in the atmosphere, not the ocean, that is very intense. So whenever we have this very, very dark green over the region of Indonesia, that means that the Madden-Julian oscillation is very intense, and that could be producing a lot of convection and precipitation, like thunderstorms, showers, and rainfall, right? But the Madden-Julian oscillation can also modify the low-level winds, and actually the Madden-Julian can produce westerly wind bursts over the equatorial region. So we can look at this just by looking at this database, and let's go look at zonal wind. Zonal wind means east or west, the eastern or western component of the wind. So let's look at this. And let's, if whenever I see this, oh, 1 second, wrong. Okay. So I have the peak of the Madden-Julian here. Let me zoom in a little bit. So the peak of my Madden-Julian or stronger Madden-Julian is located actually over the maritime continent, Southeast Asia, Eastern India, and Indonesia, Malaysia, right? So I would expect the wind anomalies in the lower levels to be from the west or red in this region, west of the Madden-Julian. So what I'm going to do, first I'm going to go to zonal wind, and then I'm going to go to lower levels, which is here, 850. Indeed. Look at my anomalies in this region. You can see the red means westerly wind bursts, all right? So in this case, in this period, all the way from January, February, into the beginning of February, we have a large area of westerly winds in the lower levels affecting the maritime continent. And look, once we got into this period, about I would say the end of February into the beginning of March, these westerly windbirds enter the Western Pacific. So I would expect, this is 2023, I think, right? I would expect, yeah, 2023. I would expect a Kelvin wave to be triggered during this time of the year, all right? Around March 1st, 2023. I would expect a Kelvin wave to be triggered in the Western Pacific. That being said, let's go back to the presentation. And for the sake of time, I'm just going to go to the answer of one of the exercises. And let's see if you guys remember once we get to the exercise. So this is this one here, I think. Yeah. So March 1st, 2023, westerly wind bursts, and look, Kelvin wave triggered. All right. So, and this was caused by the Madden-Julian oscillation. Yeah. Another thing that can cause westerly wind bursts that can trigger Kelvin waves, and some of them can trigger El Niños, are the synoptic evolution. Synoptic means weather systems that have scales of maybe 1,000 kilometers, maybe 2,000 kilometers, but not necessarily more than 3,000 or 4,000 kilometers. So big tropical cyclones, surface fronts like cold fronts, warm fronts, those are called synoptic scales systems, right? So whenever we have a tropical cyclone in the Western Pacific, either in the South Hemisphere or in the North Hemisphere or in both, they can also stimulate these westerly wind bursts close to the equator that can trigger a Kelvin wave. And again, I'm giving you the answer of the exercise. So let's see if you guys remember, but we had this like broad CAG-like feature which in the South Pacific convergence zone during this period that produced these westerly wind bursts close to the equator, and that triggered the Kelvin wave. So triggers of the Kelvin wave, Madden-Julian oscillation, synoptic systems, and even mesoscalar interactions, like tropical cyclones could be mesoscalar systems. But some of them can trigger an El Nino, but not all of them. So you need to have other things in place.
So actually, with that in mind, with your last statement, we have been receiving a few questions of how El Nino affects the atmospheric, like the Rossby waves, the Kelvin waves. So if you could go, I think maybe this is the last topic before our break, to discuss a little bit about, the interactions between MJO, Rossby waves, Kelvin waves, and if there are any difference in how the intensity or anything like that.
So I guess we can talk about this. All right. Okay. Wow, that's a complex question to answer in a short period of time because there's a lot to talk about. All right. So so MJO Kelvin waves and Rossby waves, right?
Yeah, basically any kind of equatorial waves and large scale.
Okay, so let's start looking at something that is called velocity potential, and velocity potential, it's a variable that is close to something that weather folks like us use a lot, which is called upper divergence. So it's a way of representing whether the flow is opening or it's closing. So if your mass is leaving your area or there's mass convergence or entering your area. You can think about when you're driving on a highway, if the traffic starts ahead of you starts slowing down, you have to slow down or you're going to crash, right? So that could be seen as convergence, right? But if the traffic ahead of you starts like accelerating and then you get all this extra space, then it starts opening up. That could be seen as divergence, all right? So when you think about the top of the atmosphere of the troposphere where all the clouds are, whenever you have this opening flow, that generates as favors ascent and more thunderstorms and showers and rainfall, right? So whenever we see greens, that's usually what's happening. You're stimulating more ascent and thunderstorms and rainfall, right? There's something called, there are different oscillations in the atmosphere. One of them is called the Madden-Julian oscillation, the MJO. And it's one of these oscillations that if you have it well organized, it will have one region of upper divergence in the globe and one region of upper convergence in the globe. This is called wave one because it's only one divergence and one convergence across the globe. What I'm looking in the image here is that we do have a wave one in this period, a very pronounced, actually in this period is even more pronounced, between February 7 and 13, Madden-Julian that has an upper divergence over the maritime continent and upper convergence over the Americas, right? So this is a very well-pronounced Madden-Julian oscillation. So the Madden-Julian oscillation, it goes around the globe from west to east and takes about between 1 and 2 months, depends. It doesn't always propagate at the same speed. So yeah, Madden-Julian oscillations, as we spoke before, they can also trigger these westerly wind bursts, right? Then you also have what is called a Kelvin wave. So actually, this website, and this is great. Maybe I wonder if we want to copy that on the chat, the website address. I think Bonnie already did copy it in the chat. This is very useful because this website also looks into the Kelvin waves, right? The blues, these blue contours. I don't know if you can see this. Yeah. So this blue contour means that the algorithm is saying, oh, this is actually not a Madden-Julian phase. This is a Kelvin wave. How does the algorithm detect that? The algorithm detects that because of the speed of propagation and other properties, the way the energy, the way the energy flows with that perturbation. So Kelvin waves move much faster than the Madden-Julian, also from west to east. So the Madden-Julian to propagate, The Mariana Julian is the black contour. For the Mariana Julian to propagate, it needs to interact with the rest of the ocean atmospheric system. So it's lower because it's waiting. It's like when you're working with a lot of people, if someone is really slow, then you're not going to get your work done and you need to wait for this person, right? It's kind of the same thing. So the Mariana Julian needs to wait for the rest of the atmospheric ocean system to react so it can move. So when the system is too slow to react, say if you're working in a team and someone really is not doing their job, then eventually the Mariana Julian fails, right? Dissipates, right? Because it's not getting the help from the rest of the system. But if the system is reacting somehow, then the Mariana Julian will propagate more coherently, right? So the Mariana Julian needs that. The Kelvin wave doesn't. The Kelvin wave just propagates. It doesn't care who is helping the Kelvin wave or who is not. It just moves. So the Kelvin wave is going to propagate much more rapidly. Therefore, if you're looking at one of those blue contours coming your way, and you gain confidence that that's what's happening, that's very likely going to be in your area in very few days, versus the Mariana Julian takes longer to come. In this case, this algorithm shows Mariana Julian and Kelvin waves, but they're showing the divergent part, right? When the flow is opening, so you get more rainfall. If you have a Mariana Julian and a Kelvin wave coinciding, like what you have here, this time, then your forcing for heavy rainfall is going to be even much more pronounced. So I would be scared if I were in this location during this time. Same here, right? If I were in Papua New Guinea during this period, I will be scared because we have another Kelvin wave that is interacting with the Mariana Julian poles. Now the Rossby waves, and there are different types of Rossby waves. So far we've been talking about equatorial tropospheric waves. Yeah, break. We'll take a break pretty soon after I'm done with this. But once we're looking at this, so this would be we're talking about equatorial waves, right? But when we're talking about Rossby waves, there's different types of Rossby waves. Rossby waves can go in a lot of different directions. So in this case, we're only looking at equatorial Rossby waves. And the Rossby waves in the equator, they move from east to west, from east to west. So whenever you have a lot of thunderstorms that are hitting the tropopause, those can generate a Rossby wave that moves in the other direction. The Rossby waves in the tropics are less intense than in the extratropics, and given that the Kelvin and the Mariana Julian are more prominent, then usually I don't pay extreme attention to the Rossby waves in the tropics. But sometimes will be strong enough that they can produce an impact, but you need to remember that they come from the east. And all of these can trigger westerly bursts and Kelvin waves, depending if they modify the surface flow. And with that, I think we should go on break.
Yes. It's 2:56 in the eastern United States. So
10 minutes.
10 minutes. Okay.
3:05. 3:05.
Okay. Yep. So I guess in about 9-10 minutes, we'll be right back.
Yeah. So let's meet please 5 minutes after the hour sharp, and we'll see you then. Thank you for recording. And okay, so we'll keep moving. And there's a lot of questions and there's a lot of messages, but there's certain consensus that we would like to go a little bit more with the presentation, because if you think about it, we only have 1/3 left. So I mean, there's a lot to talk about. So we'll keep going for the presentation. We have covered some of the presentation material already with the questions. So whenever we get to those slides, we will probably either pass them or just go a little bit faster. But basically what we've been doing with the question is going already to some parts of the presentation. So let's go back to the order of the presentation. So we were speaking about impacts, and I'm going to be a little bit quick with this because we have already shown you that El Nino impacts vary among time of the year. They also vary among location, and not all the Ninos and La Ninas are the same because they're interactions with other systems. So that being said, for the La Nina, which is what is developing right now, we used to expect rainy conditions in most of Northern South America, right? And then during June to October, actually Central America gets weather conditions. This is actually starting to happen right now, but interestingly, during La Nina, Mexico, for example, tends to be a little bit wetter, and this year they've had one of the worst droughts ever. So same with Chile. Chile during La Nina, it tends to be extremely dry, and Chile is flooded right now. Central Chile is. So yeah, the El Nino and La Nina are only, or ENSO is only one aspect of the climate system, it's not determinant where we're going to get. These are just some examples about ENSO. This is actually a situation that is going on right now. This is something called like it's called a Central American gyre. So this is a big rotor that forms over Central America and Mexico. Is the one I was showing you before in satellite image with the ITCC meandering to the north, and this generates a lot of rainfall. This tends to be favored during La Nina, and it's actually happening right now. Heavy rainfall associated with the gyre. This is an event, a gyre event that happened in 2020. This is the rainfall accumulated over 9 days. You can see that a location got over 1,000 millimeters, which is 40 inches. And most of this was accumulated not in the 9 days, but it was accumulated in like 5 to 6 days. So these gyres can generate a lot of rain, and they're associated with La Nina. Speaking of impacts, before I forget, I'm going to address this really quickly. There was a question about the Kelvin, the Madden-Julian, and the Rossby waves, and how do they react to El Nino and La Nina? And just to be brief, whenever we have a strong El Nino, the Madden-Julian tends to struggle propagating with strong El Ninos. Whenever you get a strong La Nina, you can also get a little bit of a struggle with propagation, but it's not as significant. Usually, whenever the Madden-Julian propagates a little bit more easily is when you are closer to neutral conditions or weak La Nina. That tends to be when the MJO propagates more easily. With respect to Kelvins and Rossbys, I don't know the answer to that. All right. We're speaking about impacts. This is just to show that there are different parts of the world that are prone to impacts. And apologies for the Spanish, just don't read the text. This is showing that, for example, in winter, an area that is prone to impacts from El Nino is central Chile, and in the spring is Argentina. So, and that has to do with different systems that modulate the weather in the region. I'm just going to jump in. Okay, and this is a question you can answer. You can answer in the chat. All right. So, and I don't know who knows this, so it's okay. I mean, it doesn't matter who knows it. You can answer. If not, you can guess. You can just guess. Pick a La Nina year and place it in the chat. Could you pick a La Nina year? It could be A, B, C, D, or E, and just put your answer in the chat. Let me look at the chat.
Yep, we're getting C, D, E.
All right. C, D.
E,
Yeah.
D or E.
All right. Good. Good forecasters. All right. Let's see the truth. Oops. Oh, I suppose. What happened here? Oh, I went the wrong way. Yeah. Yeah. Right. Correct. Whenever we have a La Nina, the hurricane season in the Caribbean tends to be more pronounced. It's the whole Atlantic, but primarily the Caribbean. And then again, there's other factors. So you've probably heard that everyone is worried about this season for the Caribbean, the 2024 season between actually right now, June and November 30, right? People are worried about it because we have a La Nina developing and the Caribbean is really warm. So this kind of configuration favors more active hurricane season in the Atlantic. The main reason is that whenever you get a La Nina in the Pacific, there's two things. One, you're enhancing a sinking branch of the Walker circulation, and ultimately, since you're modifying the Walker circulation, you tend to enhance an ascending branch over the Caribbean. But there are also changes in the vertical wind shear. Vertical wind shear is the change of the wind with height. So for tropical cyclones to form, you want very weak wind shear. You want your winds not changing too much with height, because for cyclones to organize and take control of their environment, they don't want anything interrupting them. They want a very low wind shear environment so they can organize, right? That tends to be favored during a La Nina from all of these changes in the water circulation and on the peripheral circulations associated with the Pacific cooling, right? That being said, not all La Ninas produce an extremely active season. So if you are in, let's say if you are in Belize, for those who don't know, Belize is this country in Central America. If you're in Belize, 1995, nothing happened really. And then if you're in Belize in 2001, nothing happened. There were La Niñas. So people are going to say, what are you talking about? We don't get a lot of cyclones in La Nina. But look at 2020 in Belize. They got a lot, right? So once again, you cannot just say, because we're in an El Nino or in a La Nina, we're going to get this. We need to look at other things happening. Something that stimulates the tropical cyclone season in the Caribbean as well is when the Caribbean is really warm. So if you have a La Nina, but the Caribbean is really warm, then you can get an uncanned season. But that's not the only thing as well. It also depends what type of oscillations you have in the Atlantic. It also depends how active your Western Pacific hurricane season is. And there's a lot of other factors playing a role. So El Nino and La Nina are decent predictors. They explain a certain amount of variability of the tropical cyclone season, particularly in the Caribbean, but they're not determinant again. All right, so you need to look at other things. Same with El Nino, and I do not have the example of Andrew, but 1992, we had an El Nino, and it was a really, really quiet season for the Caribbean, but we had Hurricane Andrew. Hurricane Andrew was a Cat 5, which is the highest category that you could get it at least so far in the classification of hurricanes, right? And Andrew made landfall in Miami, Florida, and destroyed a lot of homes and caused a lot of damage and killed people because he hit a populated area. So you don't really need an El Nino and La Nina to have a devastating event. So you really need to keep always that in mind. These are good predictors, but what you should also do is continue to monitor, right? Okay, I'm gonna keep going because we just talked about this. And we're going to go a little bit into background concepts once again, but I need to rush because we need to speak about some of the satellite products. So we already spoke about ocean coupling. So actually there is a concept and you could Google this for papers because I don't have one handy, but the Bjerknes feedback. So basically the Bjerknes feedback says that atmospheric changes alter the sea temperatures that in turn alter the atmospheric winds causing a positive feedback. So basically, atmosphere and the ocean, they're related. They work together sometimes. So how do the oceans and the atmosphere communicate? So the way they communicate is that sea surface temperatures, they would modulate the stability, right? So if you have a really, really warm sea surface temperature, that will tend to lower the pressures and also enhance deep convection thunderstorms. And those thunderstorms then are going to change circulations in the rest of the atmosphere. So if you really warm up the ocean, you could eventually have an atmospheric response by these changes in instability, right? On the other hand, how does the ocean read the atmosphere? The main process, I mean, there are a couple of processes really, it's not just one, but the main process of how the ocean reads the atmosphere is basically the surface of the ocean is pushed by the winds. So if you got strong surface winds, then you have a better ability to push the ocean surface and enhance an ocean current, and that will modify a lot of things. So a current will transport air mass, a water mass faster, a strong ocean current or a change in the surface ocean would also stimulate upwelling, or the rise of colder waters from superficial locations to the surface, and so on. And there's a quantity that oceanographers and meteorologists look into as well. It's called tau, the wind stress. So it's basically how the winds push the ocean surface. When we're looking at El Nino forecasting products, we look a lot at the Climate Prediction Center here at NOAA for the forecasting of El Nino, and they have a lot of great products. And one level in the atmosphere that is looked up, that is considered very frequently is 850 hectopascals. This is for weather folks, right? 850 hectopascals is basically a portion of the atmosphere that is approximately 1.5 kilometers above the surface. In meteorology, that's called a mandatory level. There is a level that in order to set up some standards so we can all look at the same data, a long time ago, the World Meteorological Organization said, okay, let's all try to produce data in this level so we can all compare, right? You cannot compare apples against pears. You need to compare apples against apples, right? So with 850 hectopascals is a level where we usually have a lot of data available. So this is one of the levels that is used to have an idea what the surface winds are going to do, right? However, when you're looking at the triggering of Kelvin waves with El Nino, you want to look at surface winds. So 850 is a good approximation to what the surface winds are doing, but they don't always behave the same way. So you really wanna 850, in 850 you will see anomalies of winds and potential westerly wind bursts, but you wanna go down to the surface to really look at what's going on. So with satellite data, there's a couple of products that are really good for that. We showed before scatterometer data. Well, yeah, we talked about it, but we have a couple of exercises with scatterometer data. We'll see if we can get there, but at least we're going to show them on the screen. And there's now there's other data from satellites that, for example, there's something called the synthetic aperture radar, or the SAR. SAR data also from polar satellites that this is another way to evaluate surface winds. And because that's what's really pushing the ocean, not the 850 winds. We have looked at this, so I'll keep going over this. We have looked at this. This is the Kelvin wave. This is another view of the Kelvin waves. So you can see the waves propagating towards the South American coast and displacing the cold air mass. So this will be a downwelling Kelvin wave, and this will be a upwelling Kelvin wave at the beginning of the frame. Let's keep going. This is another way to look at Kelvin waves propagating. So on the left side, and this comes to El Nino triggering. This is the 1997-98 El Nino, which was one of the very big ones. And on the left, on the panel on the left, you can see the westerly wind bursts. On the middle is something called the 20C isotherm. So basically, how deep is the warm water? And then on the right, you have the SST anomalies, or the anomalies of the surface temperatures. On the y-axis, we have time. This is kind of weird, maybe, but geoscientists, we looked a lot into these diagrams when you want to track things that propagate. So this is called a Hofmuller diagram because it has time in the left axis. So we can see that we have 1996, 1997, 1998. So this is time is going down. And you can see that you start getting these westerly wind bursts in this. Well, this is at I think this is at 850 hectopascals, but regardless, you start seeing these westerly wind bursts, and these trigger a Kelvin wave, right? Another burst and another one. So you start basically forcing another Kelvin waves, and eventually these warm up the surface of the ocean along the South American coast, which is here. In this right side of the image. So this is just to show quickly that how this atmospheric force in the surface winds can develop Kelvin waves. And if you want to really see the surface winds, you can look at ASCAT, or you can look at scatterometer passes, or you can look at SAR data, the synthetic aperture radar. Okay, Walker circulation. We've spoken a little bit about the Walker circulation before. So this is circulation across the equator. Basically, if you average if you make a cross section across the entire equator and average this over a period of time, along, say, a couple of weeks to longer period of times, you will see that you will tend to have these regions of ascent and descent, and this relates to El Nino. We already seen this before. This is just a different way to look at it, and you'll have the presentation. So now let's speak briefly about ENSO modes. There are two main modes of ENSO, and like everything, all ENSO events are different. So in this case, we're talking about El Nino. We're looking at El Nino modes, and there's two main modes. You have the entire basing mode, which is the Central Pacific and the Eastern Pacific warm up. These are usually the most dangerous, usually, not always, because these tend to affect broader regions, and in the South American coast and also Central America, the impacts can be very direct as well. So these are usually the most scary ones, I would say. So 1997, 98, El Nino was like that. 1982, 83, 2015, 2016, and the last one we had that is ending right now, the 2023, early 2024 El Nino was also a basing El Nino. And there's the second type, is what some people referred them as Niño Modoki or Modoki El Niños. So in this case, the warming or cooling for La Nina is usually focused more in the Central Pacific. And as you can imagine, the impacts can be very different. So these are the two main types of El Nino. Predictability of ENSO, and now we're not talking strictly about satellite data, more like models. Predictability is not good. It's not great. It's getting better, but it's not really great. And these are ENSO plumes. So we call ENSO plumes basically looking at, we're focusing on that Nino region 3.4, right, in the equatorial Central Pacific. And we are looking at how that, what the models are saying, what different model members or different models are saying about the evolution of those temperatures. So in this case, the 2014, that was the big Kelvin wave we showed you. And you see that a lot of the models are saying, oh, there's a strong El Nino developing, they're going up. And look at what happened. Look at the black curve. Nothing happened. So everyone failed there. Just maybe one or two models that maybe suggested that that was not going to happen. So 2015, the same thing. All the models were saying, oh, the strong El Nino. Some were like, maybe, and the forecasters were like, we are scared because 2014, the forecasts were wrong. And look what happened. You got a strong El Nino. So predictability is a challenge. Models are improving lately, but they can still be challenging. The time of the year when the models are challenging, most challenging, is what it's called the spring barrier or Northern Hemisphere spring. So March, April, May is when you should trust your models the least. What happens in March, April, and May is that your sea surface temperature gradients over the Pacific are kind of diffuse. They're not very pronounced. So it's very hard to represent them in numerical models. Therefore, it's very hard to tell the model really what's going on. And also in that time of the year, you tend to have the intertropical convergence zone, the ITCC, very close to the equator. And convection, thunderstorms, especially when they're organized in bigger areas, they can also generate westerly wind bursts and other circulations that affect the ocean surface. So in March, April, May, you have these two factors very close to the equator. So it's really hard to tell in which direction the system's going to go. So if you're forecasting right now, June, July, August, and later months, the predictability is a little bit better. So that issue is called the spring predictability barrier, referring to the Northern Hemisphere spring. I'm going to keep going for the sake of time, all right? Okay, part 2, satellite products to monitor ENSO. And again, you'll have this presentation. So we have some links here that for you that you could consider if you want to look at some products that could help you to monitor ENSO. Then again, we are restating this comment again. It is complicated to just speak about each instrument and what they do. In reality, the products that we use to monitor ENSO are generated by a combination of different satellite fields. So we are basically looking at end products. So there's a lot of different satellite information going on into those products. Most of it comes directly from satellites, and others, they come from numerical models, which also have satellite data. So some of the fields that we're going to look into actually have numerical model data in them. And we use observations to tune up those fields. So yeah, it's like a salad of data. We cannot say, look at this one instrument and this one satellite and use that. That applies to very few fields, all right? So let's start with the following question. What are the main fields that we can measure with satellite products? For ENSO, sea surface temperatures, this is super important, probably the main one, but sea level height as well. You know, altimetry, we talked about it. So do we have a Kelvin wave? You can look at altimetry data and see if the ocean surface is bulged or not bulged. Another is the surface winds. Yeah, you do. Model winds are actually fairly reliable, especially in the first, I would say the first 24 hours. But you also want to look at observations because occasionally your model winds are going to really be wrong. So for triggering processes in the ocean surface, you want to look at surface winds. So ASCAT, SAR, as we mentioned. Then other products, outgoing long wave radiation and precipitation products. Outgoing long wave radiation, OLR, describes the radiation that is going from the atmosphere into atmospheric systems into space. So the radiation that you're sending to space, that your body is emitting, it depends on the temperature of the body. So if you have thunderstorm clouds, the top of those thunderstorms are going to be cold. Therefore, the radiation that goes into space from those cloud tops is going to be very low. Whereas if you're in a hot desert or in a tropical location with no clouds, the temperature is going to be really warm. So you're emitting a lot of radiation that's going into the satellite. Therefore, the satellite is going to see very high OLR. So we can use OLR to infer that you have thunderstorms or clouds or clouds or rainfall. Then you have a lot of precipitation products that also could that could tell you whether you have a heavy rain producing system or a large system. Why does that matter for ENSO? You know, we're talking about OLR and rainfall. Why? Why? Because convection can also affect surface winds and can also trigger Kelvin waves and other can also modify ocean circulations that can lead. It can catapult a process that can lead to a development of an El Nino. That being said, pardon me if I jump a little bit, but I have an example here. So I know we only have 25 minutes. So let me go to an example here. I don't know who has heard about this, but unfortunately I cannot ask about this right now. But in 2023, before this last El Nino developed, this started like a coastal El Nino, right, Bonnie? Coastal El Nino along the coast of Peru and Ecuador, right? Do you know what triggered that? Oh, well, there were different things. I mean, the ocean under the surface was already warm, right? That's why another thing that we always say, don't just look at surface temperature, look at layer temperature. Of course, in the layer, there's a lot of other data coming into. You know what data also comes into the layer temperature estimates? Altimetry. Altimetry goes into that, and altimetry comes from satellites, right? So altimetry data is going into that, right? Anyway, look at layer temperature. And what happened, it does that during this period, before this event happened, the subsurface temperatures in Peru, off the coast of Peru, which is here in Western South America, were already warm. If you just look at surface temperatures, they weren't extremely warm, but the subsurface was. What happened? What happened is that we started modifying the surface flow and started inducing northwesterly flow and westerly flow. So what did that do? What is the main wind direction in this location? And I'm going to change the in color to show it. Usually the surface winds and the surface currents are from the south. So if you start forcing these northwesterly wind bursts, you're generating the same mechanism that you generate when you trigger a Kelvin wave. You're basically generating and increasing the sea level, and you're warming up the ocean surface, and you are, by limiting the southerly winds and the flow of cold air and cold water, you're warming up the ocean, and you're also indulging it, right? So what happened? This enhanced unusual westerly and northwesterly flow induced a local help to trigger the coastal El Nino that eventually entered in phase with the basin-wide El Nino. So this coastal El Nino helped to the development of the basin-wide El Nino. And you know what was the trigger? Look at this. In this product, what we're looking is at clouds at different levels. When you look at the yellow clouds, yellow and oranges, those are high clouds. So if you wanna evaluate surface winds, low level winds, you wanna look at the low level clouds, the blue and the green clouds. Those are water clouds. We're in the south hemisphere, so if you look at the circulation, you try to follow the level clouds. We have strong westerlies here, then easterlies here. So we have a cyclone there. We have a low. That was never fully classified because it's in a part of the world where tropical cyclones usually don't occur. But there was an informal classification by the Peruvian Weather Service, and they call this Yaku, which is a really non-organized tropical cyclone. It's a tropical cyclone-like structure, more like a tropical depression-like, right? What happened that we got a very strong MJO pulse in a period when the ocean surface was warm, and the subsurface in Peru was warm already. So whenever this system formed and approached the coast, it forced those easterly winds that ended up catapulting a coastal warming. And see the temperatures in March 7 in this region. This is 13 March, and look at March 20. So trust me, these values are really warm for the region. They're like 28 Celsius. And that entered in phase with the Kelvin waves that were trying to develop the basin-wide El Nino, and we ended up with the 2023-2024 El Nino from convection. Well, this is not just the cause, but one of the causes, one of the systems that triggered this El Nino was this low and this convection that was also helping to enhance the northerly winds. So see, OLR precipitation products can also help you for the monitoring of some of the processes that could help with the development of an El Nino or a coastal warming. That is where I wanted to get to. How much more time do we have? We have 20 minutes. Great. Let me go back. Okay, and we were here. We were in we were in satellite products, and now we're going to speak about surface temperatures. Again, we have a lot of surface temperature databases, and the way SSTs are computed or produced are using a lot of different techniques. So this is a whole textbook on SST data generation. However, if you look at SST fields, they are really high resolution. And if you ask me, I don't think we have a thermometer network that dense, right? So satellite data has to go to it, and it does. SSTs largely relied on satellite data and both polar orbiter data and geostationary orbiter data. So the geostationary are usually good in the sense that, again, I'm repeating this. Geostationary satellites are good in the sense that they provide high temporal resolution, so you get a lot of updates. These are not extremely critical for sea surface temperatures because it's a slow changing quantity, right? However, they will still help to get a rapid update of what the ocean surface is doing. Some of the data that is used for generating sea surface temperature from geostationary data, for example, is the 3.9 micrometer region of the spectrum in GO-16, one of the many satellites, that's channel 7. Why? Because that part of the radiation spectra, this is infrared radiation, that part of the spectra is very sensitive to surface temperatures. But then you also have polar orbiting data. The limitation with the polar orbiting data is, again, that the passes, they are not measuring one location continuously. So the data that you're going to get depends on when the satellite passes over your region, all right? So gladly, we have a lot of polar satellites. So usually we have sufficient information to fill in the blanks. Another thing, a positive of the polar satellites is that they have more instruments. They also have microwaves. So they have a better option to measure higher resolution and more variables, partly because they orbit much lower. The polar satellites orbit about 800 kilometers above the surface versus 36,000 kilometers, which are the geostationary. But anyway, these are just a very quick view of some of the different data that goes into generating SST products. In this case, we have data from Sentinel-3A, Sentinel-3B, METOP, BC. METOP are the ones producing the ASCAD data of the surface winds as well. Goes east and west. So these are polar. These are also polar. NOAA 18 and 19 are polar. The other ones are geostationary. Yes, the other ones are geostationary. So you see, you get data from different types of satellites, polar and geostationary, to produce these surface temperature fields. Then you also have another database, for example, is the OSTIA, and it's another data set of sea surface temperatures, and this is obtained using other data from other satellites. For example, data from sensors from the TRIM, the TMI, and so on. I'm going to go into details because you'll have these slides. Next, we're going to talk now about altimetry. And remember, altimetry was very useful for things like sea level, and that relates to potential presence of a Kelvin wave. These altimetry data it's also measured by polar satellites. So this is just some information for you guys to have. So some of the products worth mentioning, we had radar altimetry database systems, the RADS, from NOAA Coast Watch data portal. And this is obtained from radars located in satellites such as Jason-3, Altica, Cryosat-2, Sentinel-3A, and Sentinel-3B. See, so when we're working with polar satellites, we want to look at different satellites. Of course, you need to calibrate between them, because the more satellites you have, you're going to minimize the problem of the satellite passes. This is an example of OSCAT-3 winds. And in this case, you can see that we have problems with the passes, right? These white areas are problems with the passes. So the more polar satellites that you use to derive your fields, the more you're going to decrease this problem with the passes, all right? Okay, let's keep moving. So now we're looking into surface wind products, and we mentioned this before. One of the products that we like to use a lot is the ASCAD. This has been there for a long time. The ASCAD products, the advanced cataramer products, and these are mostly coming on from the METOP BNC, but you can also get some wind data, scalar wind data from these other satellites like Aqua, GCOM-W, SMAP, etc. Then we have the blended sea winds. This is another useful product obtained from the synthesization of observations from multiple satellites gridded at wind speeds to create gridded wind speeds. And the resolution of these winds is 10 meters approximately. Okay, we got 10 minutes to go. So this is just a quick review of some of the products. Now, once we're looking at rainfall products for the estimation of whenever we might have strong convection, these are some examples that you could use. You got the NOAA OSPO hydro estimator, then you got the JAXA GSMAP, and this is a really quick overview of some of the products that you could use, because there's much more. But the key point or the key message from this is that a lot of this information is derived from many satellites. Polar satellites are crucial for this, also for initialization of numerical models. But once you want to verify that an event is occurring, the geostationary data could be also helpful. And with this,
and just as a reminder, I've added the links to all the links on the presentation on the chat. So if you wanted to follow along and take a look at that, you can do so. But we will be sharing the presentation with the links as well. So.
All right, great. So we might have time to do a little exercise, and then I have one last thing. So actually, we're going back to something we spoke before, and it's good to go back to things to repeat, right, in training. So we have this particular situation, and we're going to look into this particular period around March 1st. Why? Because we're looking at this analysis of 850 hectopascal winds. So you can answer using the chat very quickly. 850 hectopascals, what level is that? Is that surface or is that 1.5 kilometers above the surface? You can use the chat to answer. 850 hectopascals, is that the surface or 1.5 kilometers above the surface? 1.5 kilo, 1.5. Yes,
All right.
correct.
So yeah, we're getting 1.5.
Okay, very good. Right. So that's detached from the surface. Okay, cool. We can go to the next question. So are the surface winds always very similar to the 850 winds? Yes, no, or sometimes? Are 850 winds very similar to surface winds?
All right, we're getting no. We're
lot of
getting
no's,
mostly
right?
no's. Yep.
I would say sometimes tending to yes, but no could be correct because yeah, they're never the same, right?
Yeah, we're getting sometimes, not always.
Yeah,
Yep.
sometimes probably, yeah, the grayer the better. You're always right, right? No, but in reality, yes. I mean, 850 could give you an idea, but correct. No is probably the most appropriate because they're never the same. But they could give you a good idea of what the surface winds could be, but you need to check surface winds because sometimes they're very different. All right. So just name one satellite product that could help you assess surface winds on the chat. And again, there's no wrong answers. From what you remember on the presentation, a satellite product that could help you ask. I see ASCAD, I see OLR is good. OLR is indirect because you're looking at the convection, but it's correct. ASCAD, okay, ASCAD, okay. Okay, why don't we look at ASCAD? We're gonna look at ASCAD. Okay, and we have this here. So we are worried about this region this is in the Western Pacific. And look, the equator is here, right? So let's just look at the equator right this second, okay? Just this second. And the wind scale is here on the top of the screen, all right? So let's look at the equator and tell me, would you get a Kelvin wave with these winds? This is a very open question. I want to see what you guys say. There's no wrong answer, but would you get a Kelvin wave with these winds? These are easterly winds from 5 to 10 knots. The question is open. Would you get a Kelvin wave? Would you produce an oceanic Kelvin wave from these winds? Yes or no, or whatever? Yes, 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 no, no. What's the most common? No's, I guess. Yes. Good. Okay, there's an I do not think so. I don't know. That's a very good answer, right? We're not saying yes or no. Everything is like grace. Why? Why I don't know? Why I don't know? Because I don't know the climatology of the winds for this region. So I don't know if 5 to 10 knot winds from the east is more westerly or more easterly than what we should be getting. That I don't know. Another thing that I don't know is we haven't spoken of how far south you need to have a westerly wind burst to produce a Kelvin wave. So is it only the equator? Is it 5 degrees south? If it's this is 15 degrees south, right? So you actually need an area. You need an area. You shouldn't just be looking at 0. You should be going maybe all the way down to -10 or -15 or +10 or +15. I wouldn't go further down than -10 really. Maybe -10 is or +10 degrees of latitude would be kind of close to my northern and southern edges. So actually these westerly wind bursts that are happening here around -6, these are close enough to the equator that they could help with the triggering of a Kelvin wave. Last thing, I ask a Kelvin wave, right? Downwelling or upwelling, because there are 2 types of Kelvin waves. So if you get strong easterlies, you can trigger a downwelling Kelvin wave. So yeah, it was a very open question. I wanted to see the answer. So again, see, there's no wrong answers. All right, so what I would need to do is first compare this that I'm looking to the 850 winds that I'm getting from official, well, meaning from institutions that have data calibrated. For example, CPC, if we go back to this, CPC in the Climate Prediction Center has this graphic from a long time ago, years ago, right? So this data is calibrated so you can compare what you're seeing right now with other years, previous years, and this is actually an anomaly. So according to this, if you're looking at that period, you at 850, you are getting a westerly anomaly, 2 to 4 meters. I think this is meters per second. Yeah, meter per second, 2 to 4 meters per second anomaly. So if you look at the day at the ASCAT for that whole period, then you can kind of have an idea of whether the, well, ASCAT is surface, right? So you would need to look at actually how this reflects in the surface. All right, let's go back to the next question. So we're looking at on February 26, in the equator, we have very weak winds, so I don't know. But you do have a westerly wind burst further south. Let's keep going forward in time. This is the descending path. So see, ascending and descending paths, they kind of say same things. The time is a tad different. Looking at, okay, I have 5 minutes. We have 5 minutes. Well, 10 in total, but we try to wrap it up in 5. So you see the data is kind of similar, right? So they're consistent among each other. If your data is really not consistent, is really different, then you need to look at other things because there could be a problem with the data itself. So you better look at other data sources to establish confidence that you could trust your data. So let's jump to day forward now, February 28. And now the question is going to be more explicit. Do you think this could trigger a downwelling or warm Kelvin wave? Our chances of triggering a downwelling or warm Kelvin wave higher, yes or no? Or I don't know. Yes, okay, good. I see yes, yes. Yes, yes. Okay, a lot of yeses, right? Yeah, I believe so as well. Right, Bonnie? What do you think? Bonnie agrees.
Yep.
She's nodding. I can see her. Yes, so the chances are higher. You know, the westerly wind burst, it's really far to the south at this point. It's close to -10. So, you know, a little bit far south. But if you look at the entire region between -2 and -10 of latitude, there's a whole area with surface winds with a westerly component. So yeah, the chances are higher. So what I need to do, I want to establish confidence. So I'm going to go to the next frame. Yeah, and look at the descending paths. It's even more aggressive. Now, the differences are higher. So I will doubt a little bit. You know, I know there's westerly, but I need to look at other sources of data to define whether these westerlies are reliable or not, right? But regardless, there's westerly winds. So yes, so this particular date, and this is February 28, I think, but in this particular date, yes, the chances for triggering a Kelvin wave are higher. Let's go forward. I'm just going to jump to March. Yeah. Okay. So I think these two are March 3rd, the last ones. And in this last day, the burst is gone. So March 3rd, the burst is gone. So around February 28, March 1st is when we had the highest chance of triggering a westerly wind burst. All right. So look at what we're having here. And now we're looking at February 26. What system is this? You can answer on the chat. And I need to change the cursor. What system is this? It's a northern hemisphere anticyclone, but we're in the south hemisphere. Could be a tropical cyclone, correct. The winds, I'm sorry, yeah, we cannot see the wind direction, but the winds are coming this way. This is a south hemisphere cyclone. Just looking at this, I wouldn't be able to put my hands on fire and say it's a tropical cyclone, but it is a cyclone, right? And it is relatively close to the equator. So let us go forward. And FYI, this is 850, all right? 850. February 27, you still have this. February 28, interesting. So the cyclone is retrograding, but look at the winds here. Let me go back. Look at the winds here. So close to the equator in the south hemisphere, in February 26, we have weak northeasterly, northwesterly winds, right? But look, as time goes through, since this cyclone actually, this actually looks like a tropical cyclone now, just by the winds, right? If I believe the model. Well, this is analysis of GFS, but this is embedded in a broad area of rotation. This system is intensifying, and this whole rotor, cyclonic rotor, is intensifying, and the winds to the north are responding to this intensification. And we're in February 28. Question: is this consistent with ASCA data? I'm not asking velocity, but with the trend we saw in ASCA data. Is this consistent with what we saw before? Yes or no? Or I don't know, I don't remember. You can say too. Yes, right? Yes, 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 yes. Okay, yes, it's consistent, right? So now we have a physical explanation to what we're seeing in ASCA data just by looking at ASCA. Of course, you can also look further south with ASCA. We don't have it here, but yeah. So what's going on? You do have like a tropical cyclone embedded in a rotor that is intensifying. If you recall from before, you had a Madden-Julian, a Kelvin wave, I think, going through, which tend to enhance this type of rotation. So that is enhancing your westerlies. So we're gaining confidence in that this could be real. And going back to the ASCA data, I'm just going to go back. Look at how intense the winds can get at the surface with these tropical cyclones occurring to the south. So yeah, we need to verify that this data is correct, but this is saying close to 25 knots, 25 knots at the surface. If this lasts 2 to 3 days in a long fetch on an extensive region, you can easily generate a Kelvin wave. Now, yeah, if that Kelvin wave is going to trigger an El Nino, that's a different story. And if you want to answer that question, we could stay for an extra hour, but unfortunately, we need to cut it off pretty soon because we are 5 minutes from the top of the hour, and we wonder if there are any questions or comments before we close this presentation.
Yes. Actually, I think one really important question, what are the limitations of satellite products in monitoring ENSO, and how can these be addressed in your perspective?
It's a really good and open question, a long question, and there's a lot of knowledgeable folks that are way more knowledgeable than me on the satellite aspect itself that can answer this better. That being said, what I would say is actually improving our capability of measuring a lot of this the good quality information in terms of variables that we can measure is coming from polar satellites because they can fly lower, and it's easier to place more instruments that I can actually measure the surface properly. So in an ideal world, trying to devise a satellite that has microwave instruments in its geostationary, or having more polar orbiters with microwave data would be great. That way we could measure more variables in a more, and having more data to compare and actually establish what calibrating the data so we have information that is closer to, for example, an atmospheric sounding. So I would say improving the number of satellites and sensors that can measure a microwave and retrieve more information. That's my first answer in the very short time. And of course, that leads into more like research and because there's a lot of questions that are going to appear that we don't have at the moment. So that will be my quick answer.
Yep, and we see Sheldon mentioned small satellites will be the big advance.
Yeah, see, Sheldon has a way more experience with satellite data than I do, and yeah, small satellites will be the big advance. Yeah, there's these box satellites that are producing a lot of useful data as well. So yeah, that's probably more sampling is always good. Yeah.
Right. Yeah. Yeah, I agree. I definitely agree with your perspective as well. I think that that's super important to kind of have that out there, have more research and and observations too. Unfortunately, that's not always the case in a lot of the regions, but in an ideal world as well, it would be great to have more observations to also verify.
Right. And we have 3 more minutes. So any other things, questions that you would like to address?
Not seeing question. Oh, wait. No.
All right. Could volcanic activity act as a catalyst for the start or decline of an ENSO cycle? Do we know if Tonga had any effect on the El Nino just passed? I don't know how to answer that. I have a personal perspective on that, but it's really speculation. So I don't know. That's a really good question. I don't know if anyone wants to jump in and try to answer that. I wouldn't think so, but that's my speculation, total speculation. I don't know. Right?
That's it, I believe.
Yeah. And thank you for all the comments. And I guess I will pass it along. We will pass it along to the organizers. I know probably Megan and Gary are here. I don't know if Jordan is here or anyone else would like. Bill Soberg would like to say something. Bill,
Hey, Jose,
yeah.
hey, just an interesting question. In that area, who has the strongest Met service and why?
Who has the strongest Met service in which region in the Western Pacific?
Where you were looking.
Yeah, it was the Western Pacific. I wouldn't know. I don't know that answer because we mostly work with RA3 and RA4, which are the Americas, so I wouldn't know.
There's an RSMC in Fiji, so that might be part of the answer.
All right.
I like to say they're all strong. They all have unique capabilities and strengths, and they're all serving their nationals. So great to have this level of collaboration. Thank you so much, Jose, for that great presentation. I learned a lot personally, and thank you, Bonnie, as well. And thanks to everyone who contributed to that presentation. Their names were on the slide before I had to interrupt it to just remind you that this is not a one and done. We are going to be continuing